Screen is not up. Yeah, it's coming now. Okay, 𝗕𝗲𝗃𝗃 University, Bangalore 27. Good. Vignesh. Okay, that's good. Aditya, very good. Okay, fine. So my name is Utpal and I'm going to be your faculty for your GATE exam. Okay, and I used to take various subjects. Among these, if you're from CS background, then we will be interacting for digital electronics, and if you are from EC and electrical background, then we will be seeing network theory, analog, digital. If you're from instrumentation, then all these 5 subjects will be teaching. Okay, so those who were in the last class for the network theory, just to understand how our system runs, how we take the classes, and how we are going to solve the problems, what type of concept we are going to cover, what level of the questions we are going to cover. So all these things we have discussed in the network demo. You might have seen in any other subjects demo, right? But coming to the digital, we will see how we are going to tackle the problems, what level of questions are being asked in the GATE exam, what is our syllabus, what should be our approach. So all these things we are going to see today. So the intention of the demo class is not to learn very deep into the concept. That's why we will take very small topics, mini topics, right? Which is very easy to understand by everyone in the group, right? Okay, so we will be starting the digital electronics demo, and I will pick one very minimal topic that is called a logic gate, which is the basic to be started for the digital electronics. And you might have studied in your colleges, and you might will recall if I draw the symbol of your AND gate, you will say that, okay, sir, the inputs are A and B. If these inputs will be there, this is the output, right? You might be knowing that. So what should be our approach then? What should be our approach? Let's briefly discuss the syllabus, and then we will see how we are going to uh, study the digital electronics. So if you are from the EC background, then the first topic is going to be your number system. Okay, first topic is going to be your number system. In the number system, all these things we'll see: binary, integer, floating, and it's not limited. Syllabus is not limited here. Then we will see combinational logic circuits. In this one, it is saying Boolean algebra, minimization of function using Boolean identities, right? And K-map. But if you see, we will not learn this topic, right? Minimization of function in the combinational logic. We'll shift it to other topic so that we can learn it in a sequence order. Then we are having logic gates. So it is written in the combinational one, but we will take this out, and this will be our topic one. So we will start with the logic gates, and basics of all the logic gates we will see. We will see how we can design one NOT gate, AND gate, OR gate. All these things we are going to see. What is the basic functionality of that gates, right? How that logic is behaving when the inputs are varying, that we can see. Then CMOS implementation, this will be a part of your digital logic family. Then arithmetic circuits are there. This is very high level syllabus is written arithmetic circuits, right? In this one, we will see, if you see the previous year question, most of the questions are being asked from your full adder, right? Full adder, calculate the delay. That kind of questions are there. Then code converters, multiplexer. This is the most important topic in the digital electronics. If you have seen the previous year booklet of any institute, then what you will see that if you take 10 questions, then out of that 10 questions, 6 to 7 questions are from the marks only. This is one of the most important one. Then you are having the decoders. The encoder is not written, but it is hidden here. So encoder is there. Then you are having the sequential circuits. One of the most important topic that is being asked in any interview, right? Which one is the most important? Latch and flip-flop, right? So if you sit in any interview, they will ask the first question: can you tell me the difference between latch and flip-flop? Right? This is the most important question that is being asked in the interview. Then you are having the counter, shift register, FSM, then delay, hold time, right? Critical path delay. These are there. Data converters, sample and hold circuit, ADC and DAC, and the memories, basic memories. If you're from electrical engineering, anyone from electrical? Ronak, Kambita, Bangalore 2027, Vignesh, Aditya, VIT, CSE. Okay. So if you see the digital electronics syllabus, this is also a bit limited one, right? But it is pretty hidden here, right? It's not written logic circuits, right? Does it mean we have to not read the logic gates? No, right? Logic gate, number system, so everything will be there. Computer science syllabus is bit limited, right? They don't have to learn this ADC and DAC converter. This is one of the premium topics that you will see whenever you are going to design the PLLs, right? In the communication system, many applications are there for analog to digital, digital to analog converter, right? If I'm speaking on this microphone and you are having one headset, right, and you are listening to that my voice on that headset, but in between what is my voice, which is an analog signal, which is getting converted to the digital, it is getting transmitted, and somehow it is getting converted to the analog format, and then you are listening, right? So these blocks are very, very important in the communication applications. Okay. Computer science engineering, right? They will not learn this ADC and DAC converters. Then coming to the instrumentation one, instrumentation is like it's a combination of all. If you know from EC, electrical, CSE, all they will combine and they will put in the instrumentation one. So most of the topics are here. What happened? Disconnected, trying. Any glitch you are seeing? Just type in the chat. Is it fine now? So our class is going to be very, very interactive. Okay. It's not like we'll just take one topic, we'll solve one or two questions, and then we will move forward. No, we will be solving 70 to 80% of the question in the class itself. So if you pick any booklet, maybe from EC booklet, electrical booklet, computer science booklet, and if the common topics are there, you will see that most of the questions we have already covered in the class itself, and that are the gate level question and very good quality questions we are covering in the class, right? So our class will be more than sufficient to tackle your gate exam. Make sure that you attend the class regularly. Do not miss the live class, right? Why it is important to attend the live class? One thing is regularity. You'll be regularly attending the classes, so you'll be making proper notes, right? Notes is very, very important. In our class, it's not like you'll be coming, you'll be listening here, and then you'll be going. No, there will be many questions that you'll be solving in the class. Maybe 300, 400 questions will be solving in the class itself, right? So to solve that 200-300 questions, you need pen and paper. You need pen and paper. Proper booklet should be there, proper note should be there. So once the class will, let's say today's class is getting finished, after that, whenever you are getting time, you prepare your notes so that the notes will be there with you. Whenever you wanted to revise, you need not to find the PPT. Okay, sir, this topic, where is the PPT? This topic, where is the PPT? No, PPT will be there, but I will recommend you to prepare our notes. This we have been following, at least in my class, we have been following this. So how will be our approach? Our approach will be, first we'll start with the logic gates. Then we have decoupled this part, second topic, from the combinational one, right? It is basically not falling here. So we have categorized into the second category, second topic. So second topic we'll see as the Boolean algebra and the minimization of switching functions. This is one of the very important topic, because once you are able to minimize a circuit, can you tell me why we are going for minimization? Anyone in the chat, if you're from the EC background, you should be able to answer why we wanted to minimize a function. Why we wanted to minimize a function? What is the problem? Simplicity is fine. We can simplify a network, but why we wanted to simplify? Why we wanted to simplify? To reduce the power. Pretty good. Yeah, the answer looks pretty good, but lesser gates. Correct, Rohit. You are going in the right direction. Just push yourself more and tell the right point. Just one word is there. One word is there. Okay. I will give you a hint. I will give you a hint. Okay. I will give you a hint. Suppose if you are having any digital circuit, right? Any digital circuit. Can I write the name as counter? Number of components are reduced. Noise reduction, Balakrishnan, we are going in the analog part. Noise reduction, we can say partially. Many things are there. We cannot rule out. But yeah, I'll give you a hint and then you will tell the answer. Okay. Suppose if you are designing a counter, right? What is the purpose of counter? To count the bits, to count the number of bits, right? What is the ultimate aim? What is the ultimate aim you are doing? You have to design a counter and then you have to go for fabrication, isn't it? Once you fabricate, it will come as a chip. Have you seen this in your college? Like this, like this, like this. Some legs will be there. It on the PCB, dot, 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 dot. Put it here, right? Do some wire connection, smaller layout area. Very good, very good. Suppose if you are having the lesser number of the gates, cost, that is the one that I was waiting to listen, right? Balakrishnan, very good, right? We wanted to reduce the cost. Cost to whom? Cost to the customer. Cost to the customer, right? Suppose, let's suppose I wanted to I want one counter, right? I want one counter. I went to the market. One of the shopkeeper, he is selling one brand, suppose brand one, and this is costing me, let's say, $20. Another one, it is having another brand, right? It is costing me $15, right? And they are saying the specifications are same. They are having the same specification, same output, same warranty. Nothing is going to change, right? Which one I will buy? I will buy this one only. This is the customer friendly. This is cost friendly, pocket friendly. So ultimate aim of the minimization of the switching function, the ultimate aim of the Boolean algebra, the ultimate aim of the digital mathematics. When we say digital mathematics, means we wanted to go for Boolean algebra minimization. Ultimate aim is to simplify the network. Why to simplify the network? So that we can implement the same logic with the less number of gates. We can implement the same logic with the less number of the gates. If we can implement the same logic with less number of the gates, then we will end up with reducing the cost. Cost will be reduced, right? Cost will be reduced, then we will be saving the cost. That is the one of the premium and the important point that we have to learn whenever we are going for Boolean minimization and the switching functions, right? You might have heard one term, redundant, right? Redundant logic, right? Redundant logic. Number of the compress reduces, switching time is also reducing, correct? Switching time will reduce, noise will reduce, power will reduce, many things are there, right? Suppose if you can implement the same logic with a less number of the gates, then power will be, it will consume less power only, right? It will consume less power, less heating will be there, less reduction in the battery, that capacitor discharges, many things are there, right? But the most important point which you told Balakrishna is to reduce the cost to the pocket customer, right? Customer pocket should be pocket friendly, right? So as a digital engineer, as a digital design engineer, if you don't know the Boolean algebra, if you don't know the minimization of the switching function, you should be able to deliver the circuit, you should be able to fabricate the circuit, but that circuit will be having redundant gates, right? That circuit will be having redundant logic which you don't need only, right? So redundant logic is the one that we have to think here as a digital engineer. Okay. Next is the combinational logic circuit. Here we will study adder, subtractor, encoder, decoder, mux, demux. Many things are there that we'll see. Sequential one. Here we will start with the FSM, Mealy, Moore machines. All those we'll see. We will see how FSM is there, how a flop is there. What is the difference between flop and latch, right? Is triggered, level triggered, these all things we'll see. Power consumption, delays. Then we'll go with the number system, basic number system we'll see. Then data converters, AD and the DAC converters we'll see, digital logic and the miscellaneous. Okay. So these four topics are common to the CS, EC, electrical instrumentation one, right? This will be there for your EC and the instrumentation. I don't think it's there for the electrical one. Okay. Okay, so now we'll continue. We'll take one basic logic gates. We'll try to understand the basic logic gates, and then when the will start, I think it's on Tuesday is the first class. You can check the schedule. Tuesday or Thursday will be there, the first class of the digital, where we will start in the more detailed session. Okay. So I can see 3, 3, 6, 3, 9 gates. Quickly type in the chat, what is the first gate? What is the first gate? Right? First, let's write in this order: second, third, fourth, fifth, sixth, seventh, eighth, 9. Fast response, Ronak. Ronak, you should be responding fast. In my class, everyone who is there in the class, they should be responding as quickly as you can. The first one is the AND gate, right? Very good, Vignesh. Fourth not, fourth not. Let me write fourth not. Fourth is the NOT gate. Can I call this as inverter? Definitely we will call it this as inverter. Okay. Vignesh, 3 is the XOR gate. 3 is the XOR gate. 3 is the XOR gate. Where is 3 is the XOR gate. 3 is the XOR gate. Ronak, 5 is the OR gate. 5 is the OR gate. Very good. 5 is the OR gate. 5 is the OR gate. Balakrishna, you should also be responding. 7 is the NOR gate. 7 is the NOR gate. Very good. 7 is the NOR gate. 7 is the NOR gate. 7 is the XNOR gate, right? Rohit, 7 is the, okay, you corrected it. 7 is the NOR gate. 6, no idea. 6, no idea. Okay, 6, no idea. That is good. First one is the AND gate. Okay. This one is the NAND gate. This one is going to be your XOR gate. Third should be XNOR, right? Vignesh, third should be XNOR, right? Third should be, because one bubble is there, XOR plus NOT. This will be XNOR. Okay, XNOR gate. Okay, everything is fine. These two are remaining. These two are remaining. What are these two? So these two are called as functions. These two are called as functions. They don't fall in the category of your logic gates, but sometimes we will use this as universal gate. Okay, we'll call this as the universal gates, right? Which one is the universal gate? This is the universal gates. Where is the NOR? Universal. Okay, this is a function. This is a function. This is a function. Very good, NAND and NOR are the universal gates. So this is the function, right? This we will call, suppose this is your A and this is your B. So input will be A bar and this will be B. So this will be A bar B comma 1, right? This is how we write the function. Function is equal to A bar B comma 1. A bar B comma 1 means one of the input can be 1. One of the input can be 1. Whenever we are going to design the universal gate, we will be using this, right? So this will be falling under universal gates. So when we will see the universal gate designing, then we will see this function. This is also a universal gate. So few functions are there that can also work as an universal gates. Okay, so if I take A and B, so this will be your A bar plus B comma 0. One of the leg can be 0. Okay, so how we are going to classify your logic gates? We'll classify into 3 categories: basic, universal, and the other gates. Okay, and or not. You just now seen NAND and NOR. Few functions are there that can work as your universal gates. You might not have studied in your college, but it's okay. Then XOR gate and XNOR gates are there. Okay, let's start with the first gate. We will start with the inverter. Yes, Balakrishna, any doubt is there? Function is new to me. Definitely function is new to you, and we are going to learn this. Okay, we are going to learn this, and what questions are also being previous year questions. Can you open your pen and paper and write the all these 5 things: symbol, truth table, switching circuit, diode circuit, transistor circuit. If you see the symbol of the NOT gate, right? Symbol of the inverter. So this will be your, suppose if the input is logic 1, what is the output? Logic 0, just the inverted one. If the input is logic 0, output is going to be logic 1. Okay. What is the meaning of logic 0 and logic 1? Can anyone tell what is the meaning of logic 0, logic 1? When you say logic 0, what is the meaning of logic 0? Low or high signal, 1 to 5 volt. Okay, 1 to 5 volt. 1 to 5 volt. Okay. Other answers? 0 volt is logic 0. Logic 0. 0 volt is logic 0. VCC is logic 1. Low voltage. Okay. So when we say logic 0, we mean that this is ground. We mean that this is ground. In your analog circuits, we sometimes write as VSS. Sometimes we write as 0 volt. When we say logic 1, we will write as VDD. Sometimes we write as VCC. VDD, this will be when we will read the MOS, then we'll use the VDD. When you'll use the BJT, there we will use the VCC. Sometimes the range will, let's say, 5 volt, 1.8 volt, right? And many other voltages will be there. Okay, this is what you are saying, right, Balakrishna? This range from 1 to 5. This depends on the technology, whatever technology you are using. Maybe right now, if you check the silicon labs are there, government labs, right? They are implementing I think 40 nanometer technology they are implementing. Earlier they were having 180 nanometer technology. In your college, what technology nodes you are using? In your college, you would have designed using Cadence, Virtuoso or something, right? Some tools you would have used. 180 nanometer, right? So 180 nanometer, I think 1.8 volt you would be using, right, Rohit? 180 nanometer, 1.8 volt, 91.2 somewhere you will be using, right? So this depends on the technology nodes. Okay. So truth table, it's pretty simple: 0, 1, 1, 0. Switching circuit, if the switch is, let's say, I will write as table input output. It will be very interesting class, right? It won't be boring class. It will be very interesting. Just you have to enjoy the class and with patience. Suppose if the switch is on. If switch is on, I will write as logic 1. What is the output? Bulb will be on or bulb will be off? Bulb will be on or bulb will be off? Bulb will be on or bulb will be off? When switch is on, bulb will be on or bulb will be off? On. Okay. That means when the input is 1, output is also 1. Is it an inverter? Rohit, no, you cannot make mistake. So when the switch is on, will the bulb on or will the bulb be off? Bulb will be off, right? When the switch is on, bulb will be off, right? So when we say bulb will be off, we mean that it is your logic 0. This is what exactly my next question was, Rohit. You told. What I was asking, right? That those who have attended my last class, can you tell me why the bulb will be off? Why the bulb will be off? Why? Because the current will take the least resistance path and it will flow through this short circuit path. Okay, very good. Very good. Okay. So next you can feel by yourself when the switch is off, that is logic 0. Bulb will be on. This will be your logic 1. Nothing, just one time you understand, create one good notes and you are done. Next, diode circuit. We can represent with simple PN junction diode. Logic 1. Logic 1. We will say that diode is on, but you need minimum 0.7 volt to make it on. But here we are considering logic 1. That means it will be 0.7 volt. More than 0.7, then also it will be on. We'll consider as idle diode. Then this will be logic 0. Then diode will be off. What is this one? From EC and electrical instrumentation people. What is this element? What is this element? BJT, right? It's a BJT. Okay, it's a BJT. So if the input, suppose if the input is logic 0, if the input is logic 0, transistor, this BJT will be on or off. It will be off, right? If it will be off, what is the output? VCC, right? Output will be VCC. So can we call it as logic 1? So when the input is logic 0, output is logic 1. This is pretty working as an inverter. Then we can change it. If the input is logic 1, Q is equal to on, output is equal to, output will be your ground, right? Output will be ground. VSS or ground short, right? Logic 0. This is not important for your computer science guys, right? This is not important, but yeah, you should learn basic things. You should be knowing about the electronics part, not only the digital, but basic analog also, basic electronics you must be knowing, right? Well, how you can identify a BJT, how you can identify a MOS. Obviously you should not be going inside this, find the operating point. No, you should not be going this, but basic you can understand that if I can apply a certain voltage, it will be on. On means it the switch, it will be working as a switch, it will be on. Okay, next CBE. Yes, Balakrishna, we will enjoy in the analog, right? I will ask you more questions whenever we are going for the analog one. Okay, then I will ask you what is CBE. Okay. Okay, then AND gate is like again same five points we have to see: symbol, truth table, switching, diode, and transistor, right? Symbol, truth table, these are the two important things that as a digital design engineer we should be knowing. This, if you know, well and good. If you don't know, that is also good. Okay, so symbol and truth table, these are one of the most important thing, because if you don't know the symbol, if you don't know the truth table, if you don't know the truth table, you should not be knowing how a logic gate is working. If you don't know how the logic gate is working, you should not be able to design network. You should not be able to simplify a network, right? So you cannot call yourself as a design engineer. Okay, same thing, right? Symbol is there: a b, y equal to a dot b, right? A dot p means 0 0 0 0 1 0 1 0 0 1 1 1. If you see the switching circuit, when the a is 0, means this is off. If any of these are off, then output will be off. If any of these are off, then output will be off, and if both are on, then the output will be on. Diode circuit, anyone can recall how it is there? So this will be VCC, one resistance is there, then you are having the two diodes connected like this, let's say A and B, and I will take the output from here, Y. So tell me A, B, and the output Y. When A and B, these are 0 and 0. When these are 0 and 0, will the diode be on or off? A and B. It will be on or it will be off. Just one you tell, and then I will write it. You can analyze it later. Okay. Okay. Bulb will be off. Okay. Now this is your 5 volt. One diode is there. Maybe some resistance I'll put, maybe 1 kilo ohm, 1 ohm, right? Here I will make it ground. Can you tell me this diode is on or this diode is off? I'll reframe the question. Tell me 0 volt, 1 volt. This diode is on or this diode is off? I'll again reframe. Tell me 1 volt, and I will just change the polarity. 1 volt. This will be on and this will be off. Isn't it? Right? Now you tell me. You tell me this one is at the higher potential than this one. So this diode will be on. I'm not going into anode, cathode, right? No. Okay. So this polarity is higher than this one. So this will be on. This polarity is higher than this one. So this is having 5 volt. This is having 0 volt. So this will be on. This will be short. Can you tell me when A and B, these are 0 and 0, these two will be short or not, right? This will be working as a switch on switch, and this will be short. If this will be short, what is the voltage at Y? What is the voltage at Y? When both the diodes are shorted to ground, what is the voltage at Y? It will just wire, right? It will be just a wire connection. 0, right? So Y will be 0. 0 and 1. If these are on, then it will make Y as 0. Y as 0. Could you please repeat it? Okay. So one thing you understood, this one you understood. If this is having 1 volt and this is having 0 volt, then this will be on. This one you understood or not? Okay. So if this one you understood, then you tell me. Suppose if A and B are 0, can I consider this as ground? Can I consider this as ground? Because A and B are 0, 0. So if these two are ground, right? Suppose this is your 5 volt, 1 ohm. This will be short, right? This will be a short circuit. This will be short circuit. What is the potential here? 0 volt. 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 Isn't it, Balakrishnan? Understood, right? Okay. I have to erase this. So I hope everyone understood the diode circuit. You have to analyze the diode circuit. VCC, resistance, 2 diodes, A, B, and output is Y. Analyze the circuit and fill the table. 0, 0, 0, 1, 1, 0, 1, 1. You have to fill the table. Next is the transistor circuit. Let's not make it very boring. Okay. Let's not make it very boring. Okay. So we'll not draw the transistor circuit. I will simply draw. You can analyze it. VCC, one transistor. I can keep it here. We connect it to A, and then cascade connection like this. I'll connect it to B, and then just invert it. VCC, resistance, and then take the output from here. Okay, you have to analyze this circuit for A and B. A, B, 0, 0, 0, 1, 1, 0, 1, 1. And when we will start our full class, then we will see this. Okay, everyone, whoever are attending the classes, make sure that you do this as an assignment, so that whenever I start the class, I should be getting answer. Balakrishna, you should be first telling the answer, sir. If A and B are 0 and 1, this is the output. Why this is the output? Okay, you should be telling me how this complete circuit is working. Okay, then we'll see the OR gate again, symbol and truth table we'll see, and then we'll see the NAND gate, NOR gate, XOR gate. We'll solve some questions and then we'll wrap our session for today. So let's go for symbol and truth table for your OR gate. Symbol and truth table for OR gate. OR gate A, B, and output is Y. What is Y? Y is equal to A plus B. Can I call this as plus? Can I call this as plus? A plus B? Okay, good. We can call this as plus. You can call this A plus B, A or B. You can call it anything, right? But it's not a. It's not. You cannot say it's a basic summer, right? You cannot say. But let's write it as A plus B, A or B. Anything you can make a habit. I used to tell A plus B. You can A or B. Okay. So Y equal to A plus B. Can you fill the truth table quickly? 0, 0. Can you tell me the value of Y? 0, 0, 0, 1, 1, 0, 1, 1. Tell me the value of Y quickly. All four. 1, 1, 1, 0. 1, 1, 1, 0. 0, 1, 1, 0. 0, 1, 1, 0. 0, 1, 1, 0. Is it Rohit correct? 0, 1, 1, 0. 0, 1, 1, 1. Aditya, you are not responding. 0, 1, 1, 1. 0, 1, 1, 1. Okay. So 0, 1, 1, 1. So if any of these inputs are 1, then output will be 1. Output will be 1, right? So A and B, these are the inputs, and Y will be the output. Okay. Switching circuit, you have to analyze this. Just for fun, analyze this. Suppose if one battery I have connected, A and B, OR is there. OR means two switches must be in parallel. If any of these are on, then current will pass. If both are off, then the current will not pass. This parallel network, very good. This is the parallel network. So when you say parallel network, we will enjoy in the network theory class. When we'll see the parallel equivalent resistance, parallel equivalent capacitance, inductance, we'll enjoy there. Okay. Just I will ask some random one. A, B, and maybe bulb. So 0, 0, 0, 1, 1, 0, 1, 1. Can you tell me when A and B are 1 and 0, will the bulb be on or will the bulb be off? A and B, 1 and 0, it will be on or it will be off. It will be on, right? So bulb will be on. On means it will be logic 1. Okay. Rest you can feel. Diode circuit, you can analyze the diode circuit. Transistor circuit, this also I will leave for you to analyze. Take this question. Who is going to answer first? Who is going to answer first? B plus A bar, B bar. AB plus A bar, B bar means C option is there, right? A bar, B bar plus A bar, B. A, B bar. Okay, A bar, B bar plus AB. A bar, B bar plus AB, which one? C is the option, right? C is the option, Ronak. Vignesh, you are also getting the same option C? Same option C. This is your inverter, isn't it? This is your NOT gate. So if the input is logic 0, output will be logic 1. If the input is logic 1, output will be logic 0. So if the input is A, the output will be A bar. If the input is B, the output will be B bar. Okay. This is your AND gate. Just now we have seen. So this will be A bar dot B bar. So this will be A bar dot B bar. A will come from here, B will come from here. So this will be simple AND gate. This will be A and B. A dot B. This is your simple OR gate. So this will be going to add. So A bar dot B bar plus A B. This is the option, right? A B plus A bar B bar. Okay. Next is universal gates. We can design any gates using the universal gates. So universal gates will be your NAND gate, and few functions are there, right? NAND gate. What is the functionality of NAND gate? What is the functionality of NAND gate? NAND gate is like, what is the output? If the inputs are A, if the inputs are A and B, what is happening? A and B, A B bar. Very good, Rohit. So this will be going to A dot B bar. A dot B bar. So can I also write? Can I also write like, I can redesign this one, and I can write NAND is equal to AND plus not. So I can take one AND gate and I can pass this output to the inverter, and then I will say that this is going to be my complete NAND gate. So A, B, and output will be Y. And plus not. If either of the inputs is low, the output is going to be logic 0. Let's see, Vignesh, if you are correct or not. I'm going to verify. So A 0 0 0 1 0 1 1. What is the answer of Y? Can you tell quickly, everyone? Answer Y, so that I can verify if Vignesh is correct or not. If either of the input is low, the output is going to be low. Output is logic 0. If either of the input is low, the output is okay. So you corrected it. So output is logic 1. The output is logic 1 because it's just an inverted version of your AND gate, right? Inverted version of AND gate. 1 1 1 0 1 1 1 0 1 1 1 0. So if either of the inputs, if any of the inputs are low, if any of the inputs are low, means out of these three, right? Then the output will be 1. The output will be logic 1. How we can draw the switching circuit? How we can draw the switching circuit? I can have the switches like this. And then I can connect the bulb. Okay, I'll ask some random one and then you can fill it later. 0 0 0 1 1 0 1 1. Can you tell me, for 0 and 1, will the bulb be on or will the bulb be off? Analyze the circuit and then tell. A is 0 means it is off, and B is on means this switch is on. There is no least resistance path. The current will come from here. The current will pass here. If once you start the network theory, since the wire is broken, very good. So once you start the network theory, then something called as KCL we will learn here. In this KCL, we will see that the current is there. This current is going out. Incoming current and outgoing currents are equal. Means there is no current going here. 0 ampere. So bulb will be on. The rest you can feel. Okay. Diode and transistor, high resistance path, open circuit. Very good. That is the correct understanding. High resistance and open loop. Okay. Diode and transistor, I will leave for you. Otherwise, we'll make it boring. How many of you have heard this De Morgan's theorem? How many of you have heard this De Morgan's theorem? This is one of the most important theorem in the digital electronics. This is one of the most important theorem in the digital electronics. Without this theorem, simplification is very difficult. It is very difficult to go for simplification. Everywhere we will be using De Morgan's theorem. So do we have to learn in the logic gates, or we should be learning in the Boolean algebra and minimization? In the topic 2, right? But why I kept in the basics? Why I kept in the logic gate? Because without this, you should not, correct Balakrishnan, K-map. We should not be able to solve the K-map questions. So just now, like, in order to keep this in your mind, how we are going to use this theorem, I have kept in the logic gates, right? That's what I told you. Our course structure is like, you should not be missing anything. We will learn whichever is needed early, right? In the last class, I was telling about the complex number, right? In the network theory, do we have to learn complex numbers? The answer is no. Complex number, it's a part of mathematics. Suppose if mathematics will start late, then if you don't know the basics of complex number, you should not be able to solve the AC based complex question. So complex number, basics of complex number, basics of the phasor, I kept in the basics of network theory class. Similarly here also, De Morgan's theorem, without this theorem, you should not be able to solve the logic gate questions. That's why I kept the De Morgan's theorem in the logic gate, so that the intention is not to derive this, the intention is to keep this in mind. And something every time I will be telling you, write in the short notes, right? In the whole class, whatever subjects I take, I will be telling you that write in the short notes. That means this is one of the most important point you have to write in the short notes, right? So you have to, once I write like this, write in the short notes, then you have to write this in the short notes. So De Morgan's theorem, first theorem is complement of the product of variable is equal to sum of the complement of the variable. How you have to remember is A dot B bar is equal to A bar plus B bar. Can you write in your notes now? A dot B bar is equal to A bar plus B bar. Write it. A dot B bar is equal to A bar plus B bar. Write in your notes like this. You can write X or Y, whatever way it suits you. And important is A plus B bar is equal to A bar dot B bar. Write these two in your short notes. For now, you can write it anywhere. Let's see some question, and I'm expecting correct answer from each one of you. Can you tell me? Fast response. Fast response. Rohit, what is the answer, Rohit? What is the answer, Rohit? Quick answer, Vignesh, Balakrishnan, quick answer. D. Okay. D. One thing, if you're saying D, that means Z is not there. Is it? Z not there? Z not there. Let's see. So, what is the first gate? First gate is going to be your NAND gate, right? The NAND gate means AND plus inverter. So, Y. So, I'll write as X dot Y bar. X dot Y bar. Y is coming here and Y is coming here. So Y dot Y bar. Isn't it Y bar? Y dot Y bar. This will be Y bar. Next, this is going to be your NAND gate, right? NAND gate means A dot B bar. A dot B bar. A is already Y bar, right? So Y bar A dot B. B is Z bar. So what is the final output? Y. Y is your NAND gate. NAND gate means A dot B bar. A dot B bar. What is A? A is coming from the first leg as x dot y bar A dot B. B is from where? B is from here. Y bar dot Z. Y bar dot Z bar A dot B. A dot B bar. A dot B bar. Okay. A dot B bar. Okay. Vignesh, you corrected your answer. Rohit B. Okay. Balakrishnan B. Okay. Very good. Very good. This one. After end of the combinational logic circuit, once we finish the combinational logic circuit, then this question you'll just solve in seconds only. Just tick it. 1 second, 2 second, you'll just tick it. Remember half adder you're going to implement, half adder something. Can you recall half adder when you're going to implement? This kind of circuit used to come. Answer? First answer. A. Very nice. Very nice. Very nice. Very nice. So X is here, right? This is the, here is X, here is Y. This is your simple NAND gate. So this will be X dot Y bar. Okay, X dot Y bar. X is here, Y is here. This will be X dot, means A dot B bar, A dot B. B is coming from the second leg. Second leg is X dot Y bar, X dot Y bar, A dot B bar. Coming to the second one, this is also NAND gate, A dot B bar. Is coming from the first leg. First leg is X dot Y bar, first leg dot second leg bar. Okay. First leg dot second leg bar. Final. What is the final one? F. F is going to be simple. It's also a simple NAND gate, right? NAND gate means F will be X dot X bar, X dot Y bar, bar. First leg dot second leg bar, A dot B bar. So A is this one. Suppose this is your A and this is your B. So what is your F? What is your F? F will be A dot B bar. A dot B. B is Y dot X dot Y bar bar. And then complete bar. This is what you got, Vignesh. This is what you got, right? A dot B bar. Okay. How to simplify this? How to simplify this? Just tell me one thing. Stop solving. Everyone, just stop solving. Consider this as A, right? Consider this as A. And consider this as B. This as B. So, isn't it A dot B complete bar? If A dot B complete bar is there, can I write this as A bar plus B bar? Under what condition? What is the theorem? What is the theorem? What is the theorem? Is the theorem De Morgan's theorem, right? So A dot B bar is equal to A bar plus B bar. Means the bar will be splitted and dot will be converted to plus will be converted to dot. Can we simplify this? So this will be x dot y bar dot will be converted to plus. I'll write it later. Y dot x dot y bar. This was as usual only. Whatever dot and whatever bar we have converted. Can I split this? So I have just splitted here and dot I converted to plus. One bar and one dot is there. Bar I splitted half and half. Dot I converted to plus. This is the basic De Morgan's theorem. Next. If I have one inverter, if I place another inverter, is the output going to change? Suppose A bar, I'll put another inverter. What is this? Is A, right? So can I write A? If I take double invert, this is going to be A. Isn't it here x dot y bar? It's double bar, right? Can I write like x dot y bar plus y dot x dot y bar? Y dot x dot y. It's look like XOR expression, so it was easy to look at. Yes, very good. Now, can I again use De Morgan's theorem? This one x dot y bar. So I will split this as x bar plus y bar plus y, x bar plus y bar. Okay. Now just multiply it. X dot x bar 0. X dot x bar is 0, means A dot A bar. This is going to be 0 or not? 0 into 1, 0. 1 into 0, 0. So I can split this x bar plus y bar plus y x bar plus y bar. So first and last terms are going to be 0. This is going to be 0. 0 means logic 0, not that 0. Okay. So this will be x y bar plus x bar y. Everyone got the answer? Okay, very good, right? So this De Morgan's theorem, this is very important. Without using De Morgan's theorem, this circuit is very difficult to solve. If you don't know this XOR circuit, how it is looking, then it will be difficult to solve this question. Okay, fine. Let's stop here for today, and you just watch the schedule whenever it is coming. I think it's on Tuesday or Thursday. Schedule will be there. Tuesday, Thursday, Wednesday, any of these 3 days schedule will be there, and Saturday, Sunday, one class will be mandatory. I used to take 3 classes. 2 or 3 classes I will take. In that one, 2 weekend and 1 weekdays, or 2 weekdays and 1 weekend class will be there. Okay. Anything to talk? I'll just stop the recording, and if you want to talk, you can talk.